Okay, we are just going to finish off this subsection by discussing affine coordinates. So we will look at example 5.6 and then give the definition. So example 5.6 is something that we've already looked at before. So I am just going to draw the picture. So the usual setup in A2 with x and y coordinates, and we're looking at the projective line. So all the points become lines through the origin, and we can take an affine chart where y is 1. And when we do that, we get a unique set of coordinates for, just in this case amounts to an integer, telling you how far along the line A1 you are. And we miss one point, as we said before, which is the x-axis, because that does not intersect with this line, and that's our point at infinity. But we can capture that point if we take an affine chart through x equals 1. And in that case, we miss a different point. We miss the y-axis, so that's not on there. But the value, as I say, along the affine chart that you're taking gives you what will be your affine coordinate. So so a line through the origin gives an affine coordinate, a set of affine coordinates, I should say, but well, it's in this case just one because it's just a single real number when intersected with y equals 1, except for the line y equals 0, but then that intersects with a different affine chart, which is the affine chart given by x equals 1. So we'll get different sets of affine coordinates depending on which affine chart we project to. So a line that isn't one of the axes will give one particular affine coordinate on this affine chart and a different affine coordinate on this affine chart. So we can have, so we have to specify which chart we're working in to get those coordinates. And that is the basis of definition 5.7. So let's give that. So definition 5.7, which is affine coordinates. So let AIN be an affine chart for Pn, any point P, which has these homogeneous coordinates, in the affine chart. AN has xi not equal to 0. We define the affine affine coordinates for the point P with respect to AIN by the tuple, where you divide through by xi here, and then because you've then set xi equals to 1, we can remove that point because it's just fixed, and just give that tuple. So x1 over xi, which technically should go up to xi over xi minus 1 over xi, skip the one which has the xi in it, and then continue onwards as so. And we're not going to want to we're not going to typically want to think of all of these things as fractions, so we'll just call them u1 up to un. Okay, so example 5.8, which let's continue on another piece of paper. So example 5.8, consider P, which is just going to be 1, 2, 0. So this is in P2. So these are affine coordinates telling us what, these are homogeneous coordinates telling us what line we are inside A3. And then what are its coordinates? So it's affine coordinates with respect to the first, second, and third affine charts. Okay, so this is partly a trick question, but let's go through it. So one, this is where we assume, so we say x1 is equal to 1, and fortunately x1 is already equal to 1. So you can just delete this first coordinate and you get P is just the point 2, 0 in A 2, 1. 2. This is where we set x2 equals 1, implies, so P we know is 1, 2, 0, but we're now going to divide through by 2, so the x2 coordinate, to get it so that it's equal to this. And then this is actually going to be equal to the point where we forget this one, because you know it's 1, so that should be a comma 0 in A2, 2. And the third one, as I say, is a bit of a red herring. We can't make x3 equals 1 because we can only scale by non-zero scalars, but somehow you can regard this, so, well, it just becomes a point at infinity. Okay. And just to finish off with the last remark of this section, we're just going to say is just that it is usually the case that if we do a projection to one of these affine charts, then we're going to do the last one. So usually we project to the last affine chart. And the reason for that is just because it ends in x to the n plus 1, so if you get rid of that one, then you only have coordinates x1 up to xn, which is more familiar.